Assalamualaikum, Bismillahirrahmanirrahim. Yes, hello everyone, and welcome back to my videos. So today we are going to be speaking about introduction to relief valves, and relief valves is one of the important topics that you need to consider for safety, because you're going to find them on every vessel. Okay, when you go to industry, you'll just find them on every vessel. Like you go right or left, ups and downs. I don't know if there's a down, but you're going to say there's no down, and the relief valves are usually always at the top of the vessel. So we are going to see the types of relief valves, how should they be installed, talking about when to use which relief valve, and all that kind of details. So all of that we are going to go through today. And something to consider as well, here we are covering chapter 9. It actually is chapter 9, the new book. The old book, if someone has a copy of the old book, it was chapter 8. But now we are talking about the new book, of course, where it is at chapter 9. And I'm going to cover chapter 9, Introduction to Reliefs, and partially of chapter 10, which is to do with sizing. I'm not going to go to any details of that, just to mention something generic about it. Why? Because it is important, but for chapter 10 it's not required in this course, so that's why you're not covering it. So what did we skip? We skipped chapter number 8, which is to do with the chemical reactivity, and actually chemical reactivity is one of also the very important topics. But it is also not part of the core syllabus, even though that I have the whole tendency. Actually, I would like to explain that at some time for you. Maybe after we finish our course, I'll put that as additional material for any one of you who wants to go through it and learn about it. It's beautiful. It adds to your knowledge. It's just saying that how do you know the chemical reactivity is explosive or not? So there are popular groups where you know that the chemical reactivity is very high or not, and then you can calculate that reactivity. Okay, we are back to reliefs. Yes, we are back to reliefs. So in my chapter, I'm going to cover what we have from the book chapter from the Chemical Process Safety book by Kroll and Lover. As well, what you're going to cover, we're going to cover also part of what AICHE discusses, and that was one of the presentations. You're going to find that. I'm using part of their material here, where they are talking about design considerations for overpressure protection, and here they also talk about the relief valves. And it's good to see the standards that AICHE has stated. And as part, and I don't know if you know what AICHE is, American Institute for Chemical Engineers, and I'm myself a member for many years with this leading society, and it's an international society, and it has chapters all over the world. Okay, great. So what about relief concepts? So what do you mean? What do you want to tell us about relief valves? So pressure relief valve systems are required for the following reasons. Why we want a relief? Usually want a relief because there's pressure, right? There is a lot of pressure, and this overpressure that you have, you want to like relieve it, right? You want to relieve it up. You want to get rid of it. You want to prevent it. Maybe you want to prevent it. So why? Because if this overpressure happens, so your overpressure happens, and it's collecting up here, and what happens? It's not enough for this gases passing here or here, so it still collects, it presses, and this is how it exerts pressure. It presses so hard that such that the material of this, the integrity of that vessel that we have here cannot withstand that pressure, and then okay, it blows out. Okay, so what we will say here, we want pressure relief system to first protect people, right, from the dangers of overpressurizing equipment. And we already have taken example the chapter of fires and explosions and the overpressure and what it could cause. And we want to minimize the chemical loss, of course. We protect people. We want to minimize this chemical loss from this big vessel, and we want to prevent any damage to this equipment or any other equipment surrounding that equipment, to prevent damage to adjoining property. Of course, you have a lot of properties, houses around, to reduce insurance premiums. Imagine that you have a bad plant, okay? So if you want to insure your bad plant, it doesn't work, right? They take a lot of money on that. And it's like, I don't know if I could say this, but it's like an old man when he goes to an insurance company. What do they tell them? We don't provide any insurance for you. Why? Because they know if they give them insurance and they know that he's an old man, maybe he goes to the hospital very often, and they're going to lose. They're not going to get any money out of him. Okay, so well, this is how insurance companies work, right? It's like when you're a 40-year driver, it's different from a 20-year driver where you expect more accidents from a smaller guy, right? So if you have a bad equipment, of course you're going to talk about insurance would be higher. So you want to reduce it. You want to prove to the insurance companies that we have a very good relief system. And of course, sometimes you need relief also to comply with government regulations. Okay, so you have whatever flare, you want to burn something. It's like the one we have for Benegas or whatever, Bobco. You have a big flare and you have a big flame of that. You can see the flare, it just goes higher and higher. And now and then you say, well, is this okay? Is it acceptable environmentally to burn natural gas just like that in air? What about the emissions that goes out? Okay, what about the emissions? And here what I can say is that yes, they are acceptable, and there are regulations for that. So it's not everything is acceptable. There are standards or regulations, and of course that could be also different from one country to another. So what do we have? So when we have a pressure, and here's the pressure that we have, let me read that for you. So pressures versus time for runaway reactions. Runaway reactions, like for example, you're cooling an exothermic system, and while you are cooling, so that is my exothermic system. I have a reaction, for example. This is a reactor, and this reactor, I have a cooling system. And what happened? This stopped working. And when it stopped working, this started heating up, having more gases. So your reaction is running. It's runaway reaction. So what do we have? We have a relieving vapor. We have relieving maybe two-phase flow. We have a closed reaction vessel. Okay, three of them was all applicable to that reactor thing. However, depending on the condition, how we are going to deal with that. What do I mean is that for maybe, for vapor A, if you have something that goes up and down, even within a runaway reaction, this means that there is a relief valve. So that is the relief opening pressure. So what happens? At this time, my relief valve won't opened. So there was pressure still going out, which is high, but then with the relief thing, it went down. And when it went down, now it depends on that relief opening pressure. If it is that kind of a spring that does not break as a rupture, so it's not like a disc and it was broken, it's like a spring going like on and off, and so it will return open again and then it will close and so on. Well, and you have other examples. For example, if it was a two-phase flow, you still have an opening for the relief valve, but because there is a two-phase flow, so it's not only gas, you also have liquid, which is also going to gas and producing like more and more gas. So it will still skip. It will still skip very high, and when it goes really high, as you can see here, much higher than the normal one. Okay, but we're talking about, for example, you had a closed reactor. However, this reactor is a very strong reactor and it can withstand that runaway reaction and that high pressure. So I'm saying that, well, it can withstand that pressure, and eventually what happens, the material has already finished, and because the material has already finished, I have no input. For example, if I have input, that could be dangerous as well, right? But if I talk about a closed reactor where there's no input, the material finished, so eventually it will go down. But if you're talking about a reactor which has continuous reacting, that could be dangerous, and that is not a kind of a response that we would expect. It will be higher and it could blow. Well, now this is very crowded, but I try to keep all my definitions in one page, and just to tell you that these are the main definitions. There are more, by the way, there are more. But what do you need to know? I think so it's good always to look at this figure, and then I can go back to the definitions. So what happens here, the time the pressure goes up, it reaches a certain pressure, the relief valve opens. Ooh, okay, it opens. So what is that pressure? We call this the set pressure. So the set pressure is the pressure where the relief valve begins to open. So that is the set pressure. And what happens, sometimes this really doesn't really open for some reasons, and it just goes up, and it reaches to a certain pressure. So what do we call this pressure? We call this overpressure, which is the percentage that is of the set pressure. So how much I'm having over my set pressure. Okay, how much I'm having. So if this is like, I don't know how to count it now, but if this is like 100 and it goes to 120, so I'm talking about 20% more, right? I'm talking about 20% more. But it doesn't count like that. Because this is percentage, yeah, I think so, that's fine. Yeah, it's about 20% more. Whatever, that is the percentage of the set pressure. Okay, so what about the rest? We have, other than the set pressure, which is the pressure where relief valves begins to open, we have something called the medium average weighted pressure. And this pressure, oh sorry, it's not the medium, it's the maximum allowable pressure, okay? It's a maximum allowable pressure. So we usually put our set pressure below the maximum allowable pressure that the equipment can withstand. But imagine that it also can go over that. And we call this what? We call this accumulation. And the accumulation is a percentage of that pressure in reference to what? To our maximum allowable pressure. So these are the main definitions that we have here, but of course we can also go to more definitions. Sorry. So what do we have here? Let me zoom in. Okay, so I'm going to zoom in. That's good. So what do we have here? So we have the set pressure, the pressure at which the relief valve begins to activate to open. What is the maximum allowable working pressure? The maximum gauge pressure at the top of the vessel. So that is what the equipment can withstand. However, if you want to know more information now, it is sometimes called the design pressure as well, because you're designing the vessel to withstand that maximum pressure. And usually, from experience, vessel failure typically occurs where at 4 or 5 times the maximum allowable pressure. Okay, so it will fail, it will blow if it is about 4 to 5 times. If you think about it, it shouldn't be that 4 to 5. That means there is a lot of safety factor there. So that's why this sentence here where it says, although vessel deformation may occur as low as twice. Okay. Operating pressure, that means that this is the pressure that I'm operating my system, and usually the gauge pressure during normal service usually 10% below the maximum allowable pressure. Of course, you will always operate under the maximum. Accumulation, we already said that this is the pressure over the maximum allowed pressure, and the overpressure is the pressure over the set pressure. What is the back pressure? I think it's clear by its name. So sometimes you have a back pressure from the other side on the safety valve as well. So the pressure at the outlet of the relief device during the relief process resulting from the pressure in the discharge system. Imagine that you have back pressure, and because of the back pressure maybe the valve closes, and that could cause overpressure. So we need to consider also that term there. What about the blow down? Blow down is the pressure difference between the relief set pressure and the relief reseating pressure. Okay, so it's sitting or reseating back. So we are talking about sometimes it goes up, it opens, and then it sits again, right? The relief valve sits again back, and this is expressed as also percentage of set pressure. Maximum allowable accumulated pressure, we allow for accumulated pressure, but sometimes it's not, there's a maximum for that. So it's the sum of them maximum and the allowable accumulation. It's the sum of both of them. Relief system is all of this, right? If you want to talk about the system, that means everything. So it is the relief device, it is the pipe to that relief, it is the discharge pipelines, something called the knockout drum we're going to take later, the flare, and so on. Okay, great. So what we have, we already passed through this, and this is another guideline adopted by API. It's the American Petroleum Institute. You can go and look at the standards by API. They have a lot of standards, and the one that is related to 521 are all about the relief devices. And this is the guide for pressure relieving and depressurizing systems. And actually you can see that this American Petroleum Institute, it stated this in 1997. And it's still very well known and used all over the industries. So what do you need from here? Let's look, have a look, closer look. Yep. So here it's written pressure vessel requirements, vessel pressure, typical characteristic of safety relief valves. So what are the requirements? The requirements are the things that we already have went through. Maximum allowable accumulated pressure. Maximum allowable accumulated pressure for multiple valve installation. Maximum allowable working pressure or design pressure. Usual maximum normal operating pressure. Okay, and of course this is the gauge pressure. Typical characteristics of safety relief valves. So if the pressure is 1:1, maximum relieving pressure for fire. Okay, so this is usually for fire. So it's about 116 gauge pressure. We are talking about maximum relieving pressure for process, and that could be for multiple valves. For single valves, the maximum pressure usually that is at 110. Overpressure is usually between 100 and 105. A blow down is usually at this region here. So this is like just a guide for pressure relieving and depressurizing system for for valves. Okay. Now we need to go to look at where we should have our relief valves. Do you think we should have it at the input or the output or the top? The answer is always at the top. Okay, the answer is always at the top. So if you just read the procedure for specifying the location of reliefs requires a lot of information, the review of every unit operation, the process, and every operating step. So it's not straightforward. I've just told you a generic thing. And the engineer must anticipate the potential problems. So you need to put all the problems, and they call them also sometimes the worst scenarios. Okay, you put all the scenarios that you would expect that would result in increased pressure in any place, and then you put a valve there. A relief valve. Pressure relief devices are installed at every point identified that is hazardous. That is the points where offset conditions where pressure they may exceed the maximum allowable pressure. So any place we're expecting to have this maximum allowable pressure, we put what? We need to put a relief valve. Okay, so we're simply saying for location of reliefs, put it every place you expect that there's going to be high pressure. Okay, why do you have high pressure? There are many reasons. It's like I already said that, for example, the cooling system is not working, so the pressure is building up within the reactor. But there are many other reasons why a pressure could go up. Even if you think about control systems, even the control system could go down, right? So that could be another reason that pressure could go up. Now, what type of questions we need to have in our mind. So what happens if I don't have cooling? I already talked about it, right? And it could be also because of heating, by the way. What happens? The process is contaminated, right? And contaminated, causing some kind of a reaction and runaway reaction, causing a lot of vapor and pressure build up. What happens? The operator makes an error. Instead of opening, he's closing. And I have a story with that, but there's no time for that. Maybe one day when we sit in the class, I can spell that out. What is the consequence of closing valves? Okay, so you close valves, but you block, actually, you didn't close it only, it's fully blocked, fully closed on vessels or lines that are filled with liquid and exposed to heat. So you close that vessel and you heat it up. Oh my God, it's like you're putting a can of Pepsi or Coke and you forget it in the sun. And you know what's the sun in Bahrain in summer? It goes above 50 degrees outside. Think about a closed car, closed vessel, how hot it's going to be from the inside. And I still remember that I forgot one can on my car, and while I was driving, it just started spraying me from my face. Like I was like, oh my God. Okay, so it happens. So what happens if a line fails? For example, a failure of a high pressure gas line into a low pressure vessel. So it goes from a high pressure and it goes to another vessel that I cannot handle this, please. I cannot handle it, and it goes to that vessel. What happens if the unit operation is engulfed in a fire? So if fire, that means you have vapors, you have pressure, right? What conditions cause runaway reactions? You have a runaway reaction, you cannot catch it. It's running and it's just producing more and more heat and of course pressure. So how are relief system designed to handle all this? Okay, so I just gave you many different examples that could cause generally the pressures to go up. So some guidelines for locating reliefs are summarized here. So these are some guidelines, and you're going to find that from these people here. You'll always find guidelines everywhere, right? And the ones that you see really old, these usually come from experience, and you should use it. It is good. It is good, by the way. However, there are also some new standards, which was also based on these guidelines that were built someday. All vessels need reliefs, including reactors, storage tanks, towers, and drums. All of them. So don't tell me that storage tanks doesn't need or that drums don't need. Okay, all of them. Blocked in sections of cool liquid filled lines. Okay, where there's a possibility to have a liquid line blocked, and that is exposed to heat such as the sun. That means it needs what? It needs reliefs. Positive displacement pumps. So you have pumps, compressor, it gives us pressure. And because it gives us pressure, it needs reliefs at the discharge side. Okay. Of course, the discharge side, I did not explain this, but if it comes to your mind, why it's not the input? Because the pressure that is at the output, right? So you always need, of course, that at the output of the discharge side. Storage vessels need pressure and vacuum reliefs to protect against pumping in, because for storage you're pumping in liquid, right? You're pumping in gas, so you need to protect it from what? From any blocked in, from any blockage, and you need to be careful about this storage vessel. And the next one, which is the vessel steam jackets. Well, the name just calls itself, right? A steam jacket, often rated for low pressure steam. Reliefs are stored in jackets to prevent any excessive steam. It is steam, right? You have a lot of pressure. You just feel a steam on your hand. You can see how that is burning, and you can you feel how well if you cook and use a pressure cooker. See how the steam goes out from that opening, right? So it is something that could cause a build-off or overpressure. Okay, so take an example just to refresh the terminologies that we have taken so far. So where will be the location of the relief valves in a simple polymerization process, which is in the figure below? The major steps include: we are pumping initiator into the reactor, we are heating to the reaction temperature of 240 degrees Fahrenheit, we are adding monomers when they click, and they stick to each other, they make our polymer. Okay, poly means many, of mers. This is mono, which is one, of mer. And you're adding monomer for a 3-hour period and stripping the residual monomer by means of a vacuum, and just in case using a valve, because the reaction is exothermic during monomer addition. This looks very close to my PhD reaction, but actually I had 2 monomers rather than 1 monomer. So here's the monomer where it enters into our reactor here, and because you're putting our monomer, the monomer by itself does not react, so what you need to add an initiator, and it already said that it adds an initiator. So when you put a monomer and then an initiator radical, it starts reacting. Now, talking about reaction, so I'm having a reaction that goes on here, and the heat is starting building up. I have vapors, I also have a liquid phase of the polymer, and of course this is a stirrer just to make sure that you don't have lumps of polymers from one side, it's all equally homogeneous distributed. And what do we have? We are trying to use cooling water to cool down that exothermic reaction, to bring down the temperature to the optimum temperature. So you can see the cooling water here, right? Cooling water in and then cooling water out. And this is the way how we are controlling our temperature inside this process. And then you're going to have our product. Usually it's the batch or semi-batch reaction. So you keep it till the reaction finishes, and then you open V8 to have our product. And what do we have? We have some kind of inerting. You're adding nitrogen just to make sure that you don't have any collective mixture of any cloud, explosive cloud. And actually this is not for every monomer. Some monomers are very safe to use and you don't need that nitrogen. But talking about industrial processes is different than lab scale. Okay, so what do you have here? You have cooling water in and out. Of course, you're trying to, the vapor that's going out here, you're trying to cool down the vapor, and you're collecting it in a drum. Okay, and when you're collecting in a drum, this sounds like now a CSTR for me, which is different than the semi-batch example. I'm not sure, it doesn't say there, but usually it is a batch or a semi-batch reaction. Okay, so you have a gas collected in the drum, and then you're condensing it, and of course you're trying to control the level. You're trying to control the level that is in the drum here, and of course you're going to have some kind of vapor leaving out, or you could keep some kind of using a vacuum to pull out any gas out. Okay, so this is the process here. So what are the places? Now, if you think of it, where you can have build of pressure, you can have build of pressure inside this tank, definitely. And where else? Actually, the pump is pumping product, and you have this V9 closing, or V8 is closing. V8 is closing, it's going to cause that this is to build up here, and V9 is closing, that means this is trying to push but it cannot push. So these are all places that we can have build of pressure. The gas is here and the vacuum is not working well, they have a lot of gas, and then they could have a pressure increase here. The level control is good, but if it's not working, the level could go up and up and up, and it fills out the drum, there could be a problem here. And you have steam input here, just in case that you want to cool and you want to heat as well, so there could be a build up for the steam up here. You see, like, I'm just jumping from one place to another and telling you where are the possibilities that could have build of pressure. And even the control of the pressure nitrogen that's entering, if it goes out of control, it could also cause some problem. So what do we have here? Sorry. So if you go through it, and now we just want to see what are the areas, or what's the solution of this problem. So here, if you go back to the figure, and of course you use the knowledge from table 9.1, so you go back to figure 9.5 and figure 9.6 and table 9.1. Figure 9.5, we already have seen that. This is the figure that we have 9.5, and 9.6 we're going to come to 9.6, and table 9.1, which are the locations of the relief valves. So reactor 1, a relief valve is installed on this reactor because in general every process vessel needs a relief. Okay, so that's the generic thing in table 9.1. Every process vessel needs a relief. The relief valve is labeled as PSV, the process safety valve 1 for pressure safety valve 1. What I would call that I think that's process or pressure. I think it's pressure safety valve. And we have a positive displacement pump P1 are overloaded, overheated, and damaged. Okay, these are all possibilities. If they are dead-headed without a pressure relieving device, dead-headed, that means it's pushing, but there is no output going up because of this. The valve is not working. So this type of relief is usually recycled back to the feed vessel. Okay. So we are just recycling it back, just to make sure that it's not dead. There is a flow. Heat exchanger tubes can rupture from excessive pressures when water is blocked. So where's the heat exchanger? V10 and V11. So this is V10 and V11. Okay. So there could be a blockage here. The cooling is not good. It causes that build up of vapor here because the cooling is not enough. So you don't have condensed liquid. You will have more vapors. Okay. So when water is blocked and the exchanger is heated by steam, for example, the hazard is eliminated by PSV3. Okay, PSV3 that you can see here, this is how it is eliminated, PSV3. Okay, so this is what we do. And for the head pump, you see the discharge here. Just in case that this is blocked or that is blocked, we have what? We have a process valve here. And what else? If we have build up of pressure here, what do we have? We have, you see the safety valve here, PSV1A and PSV1B. So we have two safety valves here as well. What else do you have? We're going to come this to PSV5 in a moment and PSV4, okay? Drum, again, all process variables need relief valves. And this is the reason why we are adding a relief valve here, because we have build up of gases. And we go to the last one, reactor coil. This reactor coil can be pressure ruptured. So the coil could be ruptured when water is blocked in V4, 5, 6, and 7, and the coil is heated with steam or the sun, and we need to add to this coil. So what we are saying simply is that this cooling water, there could be a problem with that cooling water. Now, it's not only the vessel is going to be heating or there's going to be a runaway reaction. It could be because that now this is going to be heated up by steam. There's no cooling in this place here. This valve is going to go off, and we could have problems that maybe that steam that I was adding, like a mix up of steam and cooling to make my temperature, to control my good temperature here. This steam could cause within this flow of the coil where it heats up the coil for the cooling water. And we are talking now the problem also on this line here. So these are the cases that we have taken. I think so it's a good example just to refresh where we can put our relief valves, and I think that sounds easy for most of you. So what are relief types and characteristics do we have? We have many types. Specific type of relief valves are chosen for specific applications, such as for liquids. So you are saying simply that relief types depends that if it's a liquid, if it's a gas, or it is a solid, it's a corrosive material, if it is vented to the atmosphere or it is vented to the contaminant. There are many variables where we can say that based on those variables we are going to identify the type and characteristics. So in engineering terms, the type of relief device is specified on the basis of the details of the relief systems. So it's not only on one part, it's a whole system that we are talking about, and the conditions, temperature, pressure, and the physical properties of the fluid. Is it a gas or a liquid? So now we just transferred all what we want to say here in what? In terminologies. What are these terminologies? Relief system, process conditions, temperature, pressure, and so on, properties of the fluid, okay, the relieved fluid, of course. And the main categories that we have here, there are two general categories, and AICHE, they also represent some categories in a different way, so that you will find things different maybe from one place to another. But just to get the idea, at least now for this chapter here, there are two general categories of relief devices: spring operated and rupture discs. Spring operated is the one that we can see here, so that is a spring. So when we have this pressure pushing out from the bottom here, it takes this to the, it's like it's pushing this, and of course this spring will be pushed, and this will open. And as it opens, you will have what? You will have the flow. Okay? You will have the flow here. So you're going to have this flow, sorry, like that. You're going to have the flow. So you will have the flow as long as the pressure is high. Once the pressure is lower, this will go down again. Now the question, you can see here there's a screw. You can tighten to make this spring even harder, and making it harder is like you're increasing that overpressure limit. I mean the set pressure. You're increasing the set pressure, the pressure at which this will open. Which means that when you increase it, that means you need more pressure here to open it. And by the way, if you think of it, well, will this spring change its properties with time? Does it change with time or not? Of course it will change with time. Any material changes with time. Every person gets old, even screws get old, even springs get old, right? So these things are also like any material, it will get old. And of course that means you need sometimes to add screwing, and of course to just to make sure that the set pressure is always right. So this is what you have here, but that is a conventional spring operated valve. That's a conventional one. You can have a balanced bellow, right, which is also balanced from both sides. Here a bellow and another bellow here. It is balanced. What do I mean balanced? Because this could go to the right or to the left. Even that the cut here looks like the cut here, but the flow is here. So this could be bent from one side. And I remember that someone was using my chair in the office for some time, and after 3 months or 2 months, I came to my chair. My chair was on the right. I don't know why, but it looks like that he was working always sitting on the right of the chair. Okay, so this is what will happen. Yeah, I think my valve is going to be like that after few times. Okay, so what I'm trying to say here, we are trying to balance it, okay, from both sides. What about the rupture disc? The rupture disc is just a disc, okay, and sometimes they also use a pin. Okay, we will see that later. So a disc, that means that is the disc, and as you have more pressure, the disc is like that. You have more pressure, the disc is like that, and then boom, okay, the disc is broken, and that will flow. And what does that mean also? It means that as it ruptures, the disc, it breaks down, even if the pressure goes down, this will still be open. So what do you need to do? You need to replace the disc. Replace the disc, and usually replacing the disc is not expensive. We use cheaper discs that you can use. So you just put a disc here, it's broken, put another one, it's broken, put another one, and so on. But it is, I cannot say preferable here, because it depends on what explosive material or what kind of gas that you're exposing here, and will you allow for maintenance here or not. So all that has a meaning as well. And here, will you allow for materials that has a lot of contaminants or not? We're going to see that. So I already had explained this, but it's always good I keep it in the PowerPoint so that you can go back to it. And what I need to add here is that you have a pressure here. but will you have a backup pressure or not? So you may have a backup pressure, and this is what it says here: the flow through the relief therefore is reduced by backup pressure. So this flow, there is a flow, but maybe there's a backup pressure which reduces this flow here, and that would affect the pressure that is affecting at that side. What about the balance below? It's balanced as we had said, and of course this flow depends on the difference in pressure of this pressure and the pressure outside, of course, and of course if there's any backup pressure it would affect. What else do you have? You have a ruptured disc. When you put a lot of pressure on that ruptured disc, it just breaks. And what important problem that you need to know about this ruptured disc, let me say that they can be made from variety of materials, including exotic corrosion resistant material. So we are just mentioning that this is made of a material like corrosive resistant, because if it is corroded, then it will open by itself. You don't need a setup pressure, or it could be a set pressure, but at a very low pressure that will be broken, and this will affect your process, of course. An important problem with ruptured disc is the flexing of the metal. So this metal becomes very flexy with time. When you have pressure, lose pressure, pressure, lose pressure, pressure, lose pressure. And what happens to this disc? It becomes very lean, very lean, very easy to get broken. Flexing could lead to premature failure and pressures below the set pressure. We already said that. Another problem with ruptured disc system is that once they open, they remain open. So ruptured discs, they are installed in series to a spring-loaded relief, and that is something that you need to know. So you cannot keep it by its own. So you want to now use it with the spring-loaded relief. Why? You want to protect an expensive spring-load device from a corrosive environment. So if you have a very corrosive environment and you want to protect your spring-loaded device getting corroded, because that is very expensive. To give absolute isolation when handling extremely toxic chemicals, okay, and again, you put it with series, that means after each other with a spring-loaded relief, just to make sure that you are isolating it from that toxic chemicals. To give absolute isolation when having flammable gases, it's all the same idea: corrosive, toxic chemicals, flammable gases, and to protect the complex part of the spring-loaded, to relieve slurries that may plug spring-loaded devices. So maybe slurries, they spoil the spring, and not to spoil up this spring, what should we do? We use this ruptured disc. So the ruptured disc does the whole job in support to the relief, to the spring-loaded relief. Okay, so what else do we have? We have three subcategories of spring-loaded pressure reliefs. Three subcategories. The first category is the relief valve. The second category is the safety valve. The third one is the safety relief valve. Oh my God, I thought all of them are the same. Okay, they are. Talking about the same, you could say that, but actually we always try to make things systematic and defined very clearly so that we know what you're talking about. A relief valve is primarily for liquid service. The relief valve, liquid only, begins to open at the set pressure. This valve reaches full capacity when the pressure reaches 25% over pressure, which means the pressure over the set pressure. The valve closes as the pressure returns to the set pressure. Easy, easy. The safety valve is for gas service. So when I say safety, not relief, safety valve, I mean gas. Safety valves pop up when the pressure exceeds the set pressure. This is accomplished by using a discharge nozzle that directs high velocity towards the valve seat. After blowdown, that means I got rid of all the excess pressure. The valve resets, it sits down again, the valve, at 4% below the set pressure. And the valve has a 4% blowdown. Okay, as you see, 4% below the set pressure. Again, just to go back. So this is the seat, okay? This is where it sits. So this is the place where this piston is sitting. Okay, so what we are saying that if the set pressure is 120, so 25% over 100, say it's 100, just to make the calculation easy. So if it is 100, this 125, this will open, and after it goes down, it will go about to 96 till that sits down, okay, which is like 4% less. And that's what it's saying, that's 4% below the set pressure. The valve has a 4% blowdown. The safety relief valve, it has both words, safety relief. Okay, so we can say that's for liquid and gas. Safety relief valve function as relief valves for liquids and as safety valves for gases. It works for both. Okay, and this is why we always use safety relief valves. And now you go back here and see what do we have. The same example, the relief valves, the safety valves, safety relief valves that we have all over place. Now we already said that we have PSV 1A and PSV 1B. So you can see here PSV 1A and 1B. Oh my God, what is the difference between these two? We know this shape, which is the normal safety valve, and that is the normal safety valve for what? For the spring. That is for the spring, What about the one here that we have? The one that we are having here, that is the rupture disc, okay, and which is in series in line with the spring one. Why did we put it here? Because here's the main pressure, the material that we are really using here, or the reactive material that we have in the reactor. So PSV1A is the rupture disc to protect PSV1B from reactive monomers. Clear. PSV1B is the safety relief valve because a runaway reaction will give two-phase flow. Okay, so you see, we say safety relief valve because we have here a runaway reaction. If the cooling stops, we will have two-phase flow of liquid and vapor. We have liquid and vapor inside the polymerization reactor. PSV2 is a relief valve only because this relief is in liquid service only. Where is PSV2? Where's PSV2? Here's PSV2. We have only liquid. Here, as we said, we have the polymer is here. This is our polymer, and my polymer is getting out here. So that is liquid, right? That is liquid. So that will be a relief valve. If PSV3 is also a relief valve only, and a conventional one is enough. So whereas 3 is up there, so I have cooling water. So because it's water, it's only relief valve. PSV4 is a safety relief valve, and because liquid or service is possible. And let's see what is PSV4. PSV4. Did you find it? Yes, here. And because we have, as we said, we are condensing, we're having liquid here, so we may have droplets as well going out from here. So I mean, not droplets, sorry. If this goes up and up, the liquid could go out, or if you have a lot of gas, the gas could go out. So you have a two-phase. So we need what? We need a safety valve because liquid or vapor service is possible. Because this vent will go to a scrubber, now we don't know what scrubber, with possibly large back pressures, a balanced bellow is specified. Okay, so here we are suggesting to use a balanced bellow. Why? Because we have a large backup pressure because of the system that's coming later from this process. PSV5, just to think about the balanced bellow, it came to my mind. Imagine that it does not sit right back to its seat. And because of the large backup pressure, the balanced bellow should make sure that it sits right on its seat. So I just wanted to mention that. PSV5 is a relief valve for liquid service only. Liquid service only. Why? Because we have only liquid here, cooling water liquid. Okay, so these are the locations of the things that we have taken. What else do we have? I mean, just to extend our knowledge, what else do we have? We can see you have a pressure. You have this kind of a safety valve where it has a pin. You see this pin? This is a flat pin. Flat. مسطح يعني flat pin. Okay, it's like a very flat. I don't know how to draw this, but because it's very flat, it can get broken. Okay. And the major advantage of the pin relief is that the pin buckles okay, at a precise pressure. And the major disadvantage is that when the pin buckles, خلاص, okay, the valve opens and it stays open. So it's very similar to the rupture thing, and they usually use it. Sometimes maybe it's simpler to change this rather than changing something that is directly in contact with the system. Now it is not in contact with the system, it's from the top there. Okay, so that is the idea. We are trying to keep it easier for changing and maintenance. There are other operated reliefs called the pilot operated relief valve, and again, you're pushing here. I may not go into the details of this because it has some kind of a complex operation here, but if you can see that there's a spring here, and mainly that we have a spring, and we have also a large piston at this side here, and the reason that we have this kind of pressure is the kind of it helps with the balancing the pressure as well, for the valve to sit very perfectly in its place. And what else do we have? We can find out here, it's written, the pilot valve exhausts either to the outlet of the main valve or to the atmosphere. Pilot operated relief valves are commonly used in clean surfaces. So this is one kind. I don't think so we have any more thing to say. So we have, it's pushing here, this spring opens for it to exhaust, okay, to exhaust. If you push this up, and what do you have? You have this this pressure pushing from here, and this piston will go up, and as it goes up, you're going to have the vent outlet. Okay, what do we have? One of the things that we do have with valves is that they chatter. Okay, they chat. They chat with each other. No, they chatter up and down, okay? They play. And what do we mean by chatter? It happens if a system is not designed correctly, okay? They may chatter violently. Make it clear for us, please. Chattering is the rapid opening and closing of a relief valve. It opens, it closes, it opens, it closes. Why? It's because maybe you have put a wrong valve in that place. That can cause, of course, the seat damage. Valve like opening and sitting again, but hitting, of course, the seat. And that could be a problem, and it could cause a mechanical failure. The major cause of the valve chatter is the oversized relief valve. So you're oversizing it, okay? And what do you mean by oversizing? Actually, this is what it means here. It's written, the valve opens a short time to reduce the pressure. So you oversize it. That means with a very high pressure, it started opening, and actually it should have opened before. So now when you reduce the pressure and it closes, and then it goes up again. Why? Because you did not put off the pressure enough. And the pressure then rises rapidly to open the valve again. This pulsating action can be destructive. The major causes of chatter are excessive inlet pressure drop. There's a lot of inlet pressure drops, or high backup pressures, or oversized valves. So these are the main reasons, and all of them go back to the difference in pressures that causes this valve to open and close. So these problems have solutions. For example, excessive inlet pressure drops can be prevented with large inlet pipe size. So if you have a large inlet pipe size and fewer elbows, you can put off this difference in pressure. High backup pressure can be prevented by increasing the size of the exit line. Okay, so the exit line has it's big pipe, so that I can have less backup pressure, so that I don't cause it to close again because of that backup pressure. Oversized valves, of course, that means I need to design it correctly. So what are the advantages of various reliefs? We already talked about the advantages and disadvantages, but just to have a quick look about it. So what do we have? Spring operated conventional. Advantages for the spring is good. It resists at pressure 4% below the set pressure, that's that blow down. The disadvantage is it's affected by backup pressure and can chatter with high backup pressure. What about the balanced bellow? It's not affected by backup pressure because it is balanced, and handles higher built-up pressures because it likes both sides That's why its handles build up backup pressures really strongly and protects spring from corrosion. And here, what are the disadvantages? This bellow, by time it gets fatigue, like because it goes up and down and up and down, it gets fatigue, it ruptures. Flow is a function of backup pressure, that's for anything there. May release flammable toxics to an atmosphere. And I forgot this, I didn't have that in mind actually, but this is something that I did not have in mind that could happen. Ruptured discs, we already said that is low cost, easy to replace, good for high volume releases, less fouling, it's always good, right? No seal leakage, but what? Stay open after relief. That is the main problem. It stays open after relief. But it was designed to do this, okay? So we're just mentioning that this is a disadvantage so that we can take care of that disadvantage by another relief valve or safety valve. Okay, and of course we have some fatigue problems if it opens, but it does not break. It opens and does not. It's not really opening. It's just moving up and down, up and down, up and down, and so on. Okay, the buckling pin is very similar as we said to the rupture disc. So the thing that we need to mention here that the temperature for those pins that we have, it cannot exceed 450 degrees Fahrenheit. Other than that, the initial cost of the pin is much more than the rupture disc as a disadvantage. What about the pilot operated? I did not explain that a lot, but we said that this is one of kind of a system that can we have. It operates really well, can operate up to 98% of set pressure because of the pressure that comes from more than one side. But there's a lot of plugging that could happen because we are apping to more than one opening within the system of this pilot valve. Great. So we have the relief scenarios. So up to here we are going to stop for our first video. We took the types of the valves and what are the advantages and disadvantages, and we have taken examples with that. And the next video we are going to talk about the relief scenarios and the rest of this chapter. So till then, I thank you very much. This is Dr. Bassam Hamad, and I hope you a very pleasant day and life. Ma as-salama.